Hello and welcome to another video of Wise Interactive Learning. In this video, we are going to mainly see what is higher order derivatives. So first we'll Hello and welcome to another video of Wise Interactive Learning. In this video, we are going to go through only one concept of higher order derivatives. But in this whole topic of the covering of higher order derivatives, we are going to see what is the purpose of it, and we are going to go through the examples which are based on our syllabus. We are obviously not going to see what are the examples based in real life and how they can be implemented, but rather we are going to see the basic outcomes of how the terminology is used in our syllabus. But before we go on to that, we need to learn what is the basic concept of higher order derivative. So initially when we learned f of x as something as y, or we call it as a function which can be anything like x square. So this is a basic example, right? So your graph would be something like this and you call it as y equals to x square. And we have been over here multiple number of times, but what we don't understand is what is its implication, like what is it defining us to. So what we took it as, like we defined a point to it and we said that if we want to know the slope, we need to get the derivative of it, or rather we need to check what is the change in y with respect to change in x. So dy upon dx means nothing but it is the change in y upon change in x. So when you draw actually on graph, it is going to give you the slope of the particular function. But if we take the slope of a function and let's suppose that again we want to have another derivative of it, what is it us giving exactly? Like what is the main purpose? Like if we take a slope of a curve and then again we differentiate that same curve, what is going to imply from that? And the answer for this is very simple, and I'm going to tell you from a very easy example. For example, if we take displacement, or let's take if a car is running at 80 kilometers per hour. So what does this depict, right? So first we have something called as displacement. So S is nothing but displacement, isn't it? So when we try to differentiate it with respect to time, and let's say the displacement is on x-axis and the time is on y-axis. Sorry, it should be other way around. So let's say that the displacement is on y-axis and x is on, and the time is on y. So let's say that the displacement is on y-axis and the time is on x-axis. So if we have to check what is the displacement with respect to time, we have to necessarily get dy upon dx on a particular graph, isn't it? But what will this give you? It will essentially give you dy upon dx, or rather ds upon dt. In other words, it is going to give you velocity, isn't it? And what do we mean by velocity? Velocity is nothing but the exact ratio of how much a car or a vehicle is moving per time, right? So it is the exact measurement with respect to time. So if a car is moving with 80 kilometers per hour, and if we take a hypothetical ideal situation, and if that car is running exactly 80 kilometers for 1 hour, it is going to cover 80 kilometers at that speed, isn't it? But what is the purpose of higher order derivatives? So the purpose is when you differentiate velocity. So see, first we have differentiated displacement or distance. Now we are differentiating the velocity. It will give you acceleration. So once you accelerate more, it is necessarily meaning that we have more velocity into our car, and this is the exact meaning which we have over here in the higher order derivatives. It is nothing but when you take a function which is, let's say it is x or y or anything. So when you take dy upon dx, so you are necessarily differentiating the function y with respect to x. Then what we are trying to say is, in the higher order derivatives, let's say if the first order is dy upon dx, so what do you think that it is second order derivative is going to be? We can directly say that it is dx of dy upon dx, isn't it? But this is very complicated and tiresome to write. So we have found out a exact right method to write it, and it is nothing but d2y upon dx squared. And the main purpose of writing this over here is that if you see that this 2 exactly signifies what is the order of the derivative. So the third will be d dx of d dx of dy upon dx, and obviously you are not going to write this in such a way, so you are going to write it d3y upon dx square. For our courses, we are going to see only till the second higher order differentiation. We may go for higher third and fourth differentiation if it is required, but I don't think so at this point of time we'll need those. So we'll take few examples in the next few moments, which is the first example is x log of x, and the second example is going to be e raised to 2x tan of x. Obviously these are solved examples, I'm just going through them to have a grip of it, and since they are solved, if you are not getting my way of teaching or not understanding the way I am explaining, you can obviously refer it to your solved examples. So let's take the first problem, which is y equals to x log of x, and I'm right now from this moment of time I consider that you understand all the techniques which I have told you in the previous video. If you have not watched the previous video, make sure that you hit the I button. You'll get all the videos linked over there, or you can go on to my channel where you find all the videos. So I'm going to do it in a fast way. So dy upon dx shall be x times x divided plus log of x. So this is your first, which is 1 plus log of x dy upon dx. So dy upon dx, so I'll again rewrite it. Dy upon dx is this. So what will be d2 upon dx? d2y upon dx squared shall be 1 plus, so it's 0 plus 1 upon x. So this is your final answer for x log of x. Now we'll see what is the second. Now we'll see the second example, which is y equals to e raised to 2x times tan of x. This is a bit confusing, but it is make sure that it is very easy to understand. A lot of people will jumble up over here, trying to find out by which method we are going to solve this. So it is fairly easy. We have dy upon dx, so we are going to solve this in faster way. So if we keep e raised to 2x as constant, it is going to be sec square x, because the differentiation of tan x is sec square x. Now we have to keep tan x as constant. We have 2 times e raised to 2x. So this is your differentiation of e raised to 2x. So again we can differentiate this, but we know that we have e raised to 2x as common over here, and differentiating it again and again won't make sense. So what we'll do is we'll take e raised to 2x as common, isn't it? And what we can say that here, if you see, I'll again write the same term before doing that, and here you can see that e raised to 2x something over here, and tan x, it is nothing but y, so we have 2y over here. Now we have dy upon dx on the left side. So now you can just differentiate this function, which is e raised to 2x sec square x, and you can say dy upon dx can be written as the same term. So d2y upon dx squared, so e raised to 2x as it is, so sec square x differentiation will be 2 sec of x times sec of x times tan x, plus now we have to take sec square x as constant, and then 2 times e raised to 2x. isn't it? Then plus we have 2y, so we have 2 dy upon dx. Now be careful that dy upon dx, so we know what is dy upon dx, so this is this particular function which is the whole term, so we can again rewrite that same term and we'll find the answer. So we have d2y upon dx squared as, so from the first line over here what we have is 2 sec square x times tan x times e raised to 2x plus, now we have e raised to 2x 2 times sec square x plus 2 times the whole dy upon dx terms. So dy upon dx terms is nothing but e raised to 2x times sec square x plus tan x times 2 plus e raised to y, and we have to write the whole term, so e raised to 2x as it is, and then we have sec square x plus 2 times tan x times e raised to 2x. So this is your original term from here, and now we can simplify this. So your final answer will be, so if we look over here, in all these terms we have one common term which is 2 e raised to 2x as common, right? So 2 e raised to x, 2 times e raised to 2x, 2 times e raised to 2x. So what we can do is we can take 2 e raised to 2x as common and we can write all the other terms in one format, sec square x times tan x. The second term will be sec square x, then again sec square x, we have 2 times sec square x, then we have tan x. So this is your final answer. Now we'll see the another 2 to 3 problems based on the same, which is in the next video. But in the next video what we are going to go through is, we are going to go through multiple number of questions, around 10 to 15 questions based on different problems. It can be from composite functions, it can be from logarithmic, it can be from inverse trigonometric, it can be from parametric, it can be of higher derivatives, or it can be of implicit functions. So in entirety we are going to cover up all the second chapter in one video by just solving all the different questions. So for CBSE people I am going to upload a different video, and as opposed to Maharashtra State Board people I am going to upload a different video, since the syllabus is a bit different. Rather you can also do this by watching multiple number of videos. You can also watch the CBSE if you are a board, state board, Maharashtra board people. You can also watch of Maharashtra board people if you are a CBSE, and vice versa. So in that case just make sure that you watch the next videos. Thanks for watching. See you in the next one.